iLearner. Learn today, lead tomorrow.
Hey there. Ready to dive into a world where buildings stand strong even when things go boom?
Sounds intense.
Today, we're exploring design of blast-resistant buildings in petrochemical facilities.
Oh, yeah, that one.
And let me tell you, this book is no lightweight. It's packed with practical advice, detailed calculations, even real-world case studies.
It really is. It bridges the gap between theory and application.
You can tell the authors are seasoned engineers.
Been in the trenches for sure.
And they share their expertise in a way that's comprehensive and accessible.
Yeah. You're not just getting equations thrown at you. They walk you through the whole process of designing a building that can withstand those incredible forces.
Step by step.
Exactly.
Right from the start, they make it clear this book is all about mitigating risks in the petrochemical industry.
Absolutely.
While preventing explosions is the ultimate goal, being prepared for the worst-case scenario is absolutely crucial.
Couldn't agree more.
Okay, so before we get into the nitty-gritty, can you give us a quick overview of the book's structure? What are the main themes and how do they flow together?
Well, the book is laid out in a very logical way.
Okay.
Almost like a roadmap for blast-resistant design.
Like a dirt map.
It starts with the fundamentals. The different types of explosions, how blast waves behave, how materials respond under those extreme loads.
Makes sense.
Then it dives into the actual design process,
Okay.
covering everything from analyzing those loads to detailing the connections.
And they dedicate a good chunk to retrofitting existing buildings.
Oh, yeah, absolutely.
Which I think is super relevant for anyone working with older facilities.
Couldn't agree more.
They even provide a few detailed design examples walking you through the calculations.
Yeah.
Showing you how these principles are applied in practice.
It's like having a virtual mentor guiding you through each step.
That's fantastic.
Yeah.
And just to be clear, our conversation today is just our interpretation of the book's contents.
Right.
We highly encourage you to grab a copy and dive into the details yourself.
Absolutely. Now let's jump into chapter 1, where the authors set the stage for blast-resistant design.
Okay.
They highlight the unfortunate reality that accidental explosions, while rare, do happen, and the consequences can be devastating.
And they don't shy away from using real-world examples.
They don't.
Like the 1989 explosion in Pasadena, Texas.
Right.
Where a vapor cloud explosion caused significant damage and tragically loss of life.
Really drives home the point that we're not just dealing with abstract concepts here.
Yeah.
We're talking about protecting people's lives.
Exactly. So distance is our friend.
For sure.
The farther a building is from potential hazards, the safer it will be.
Yeah.
But that's not always possible, is it?
Right. That's where the concept of blast resistance comes in.
Okay.
We need to design buildings that can withstand those pressures and protect the occupants inside. And remember, it's not just about the blast wave itself.
Right.
Projectiles fires, even ground shocks can also cause significant damage.
It's like a multi-pronged attack
It is.
that the building has to be prepared for. So how do we approach this whole blast-resistant design process? Seems pretty daunting.
The authors present a very methodical approach, breaking it down into a series of steps.
Okay.
It starts with identifying potential hazards, quantifying the risks, then moving on to analyzing the structural design and detailing every element.
It almost sounds like detective work.
It kind of is.
You're anticipating every possible scenario.
Yeah.
And building in safeguards.
Yeah, and they emphasize that this is not a solo mission.
Right.
It involves collaboration between process safety specialists, design engineers, and everyone in between.
Collaboration is key.
Absolutely.
Now, in Chapter 2, they dive into some general considerations.
Okay.
They highlight how the need for blast resistance has evolved over time, driven by those unfortunate incidents we mentioned earlier.
Right.
And they point out that the petrochemical industry itself has become more complex with larger plants and a wider range of hazards.
It has.
This means a one-size-fits-all approach to blast resistance simply won't work.
Definitely not.
They stress that the decision of whether to design for blast resistance and to what level ultimately rests with the owner. And that decision should be based on a thorough risk assessment.
Absolutely.
Considering factors like the distance from the blast, source, the building's function, and the number of people inside.
All important factors.
They give a great example of a control building.
Yeah.
If it's located far away from potential hazards, maybe you don't need to go all out on blast resistance.
Right.
But if it has to be close to the action because of its function, you better make it super tough.
It's all about a tiered approach.
Okay.
Based on a careful evaluation of the risks. And they even mention a couple of industry standards like the CCPS building guidelines and API RP 752,
Okay.
which can guide owners through this process.
So we've talked about the why and the when of blast-resistant design.
Right?
Now let's get into the what. What are the
fast.
different types of explosions we need to be aware of?
Chapter 3 dives into the heart of the matter,
Okay.
explosion basics.
Love it.
The authors break it down into 4 main types that are common in the petrochemical industry.
Oh.
Vapor cloud explosions, pressure vessel explosions, condensed phase explosions, and dust explosions.
Let's start with vapor cloud explosions, or VCEs.
Okay.
These are the ones we often see in the news, right?
Yeah,
A massive cloud of flammable vapor ignites, and boom.
exactly. The authors highlight the 4 key ingredients for a VCE.
Okay.
Release of flammable material, delayed ignition, a flammable fuel-air ratio, and something to accelerate that flame,
Gotcha.
creating those dangerous overpressures.
I imagine congested piping or a multi-level structure could really intensify those flames.
Absolutely. And they also touch on other fascinating types of explosions like the BLV or boiling liquid expanding vapor explosion.
Oh, wow.
Think of it as a pressure cooker gone wrong,
Uh-huh.
resulting in a massive fireball and a powerful pressure wave.
That sounds terrifying.
It can be.
And then you have dust explosions,
Yeah.
which are surprising to many people.
They are.
It's amazing how a cloud of fine dust can become explosive.
It is. And they point out that if that dust is mixed with even a small amount of flammable gas, you get what they call hybrid mixtures,
Interesting.
which can be even more intense.
It's like combining 2 explosive ingredients into one super powerful cocktail.
Exactly. And don't forget about physical vapor explosion.
Okay.
These happen when 2 streams of stuff at very different temperatures suddenly mix,
Like,
like molten metal and water.
oh, wow.
That creates a rapid expansion of vapor and a powerful explosion.
Okay, so we've got a good handle on the different types of explosions.
All right.
Now, how do we actually measure and characterize these explosions to understand their impact on a building?
That's where we start talking about blast waves,
Okay.
which are essentially moving walls of pressure generated by an explosion.
Okay.
The authors describe these waves using parameters like overpressure duration impulse, shock front velocity, and wavelength.
Hold on.
Let's do any term.
I'm getting flashbacks to physics class.
Ah,
Could you break that down a bit?
sure.
What do those terms actually mean in the context of an explosion?
So think of it like this.
Okay.
The overpressure is the difference between the peak pressure of the blast wave and the normal atmospheric pressure.
Okay.
The higher the overpressure, the more powerful the blast.
Makes sense.
The duration is simply how long that overpressure lasts.
Okay, so a short, sharp blast with high overpressure would have a different effect than a longer sustained blast with lower overpressure, even if the total energy released is the same.
Exactly. And the impulse combines those 2 factors,
Okay.
giving us a measure of the total force delivered by the blast wave over time.
So a higher impulse means a bigger punch, so to speak.
Right. Then you have the shock front velocity,
Yeah.
which is how fast the leading edge of that pressure wave is traveling.
Uh-huh.
And finally, the wavelength, which is basically the length of that pressure wave from front to back.
Okay, I'm starting to see the picture. These parameters help engineers quantify the destructive power of a blast wave.
Yes, they do.
But how do those waves actually interact with a building?
That's where it gets even more complex.
Okay.
The authors explain how blast waves can be reflected, diffracted, and even create dynamic wind pressures as they interact with a structure.
Okay. Reflection seems straightforward.
Mm-hmm.
The wave hits the building and bounces back, potentially amplifying the pressure.
Right.
But diffraction,
Yeah.
that's a little trickier.
Imagine water flowing around a rock in a stream.
Okay.
The blast wave doesn't just hit the building head-on.
Uh-huh.
It flows around the sides and over the top, creating these complex pressure patterns.
And then you have dynamic wind pressure.
Yes.
Is that like the wind pushing on the building?
Yes. But this wind is generated by the blast wave itself.
Okay.
It's a force that acts in the direction of the wave's movement, adding to the overall pressure on the building.
Wow. So it's not just one force we're dealing with.
Right.
It's a combination of all these different pressures and loads acting on the building from all directions.
Exactly. And to make things even more challenging, the authors highlight a couple of often overlooked factors: negative pressure and rebound loading.
Negative pressure.
Yeah.
So the building is not just getting pushed, it's also getting told.
Right. Negative pressure or suction happens in the wake of the blast wave
Uh-huh.
as the pressure drops below atmospheric levels.
Okay.
And then you have rebound loading,
Okay.
which happens when the building, after being pushed inward by the blast, springs back.
So it's like the building is getting squeezed, then stretched, then shaken.
Exactly. And those negative pressures and rebound forces,
Right.
while often smaller than the initial blast load,
Yeah.
can still cause significant damage if they're not accounted for.
Okay, so we've got our different types of explosions, and we understand how blast waves behave.
Mm-hmm.
But how do engineers actually determine what blast loads to design for?
Well,
Because realistically, there's no way to predict exactly when and where an explosion might happen, right?
right. It's all about risk assessment and using data from past explosions to make educated guesses.
So what are some of the methods they use to calculate those blast loads?
They discuss a few different approaches. One is the TNT equivalency method,
Okay.
which they point out isn't very accurate for vapor cloud explosions.
So it's like comparing apples to oranges.
Exactly. Then there are more sophisticated methods like the Strelo curves, which take into account the speed of the flame, and the multi-energy method.
Okay.
These provide a more nuanced picture of the blast wave and its potential impact.
And they also mention computational fluid dynamics, or CFD, which sounds incredibly high-tech.
CFD is a powerful tool that allows engineers to simulate the propagation of a blast wave through a complex environment.
Okay.
Imagine all the pipes, vessels, and other structures on a petrochemical site.
Yeah.
CFD can model how those obstacles affect the blast wave and predict the pressures on a building with much greater accuracy.
It's like a virtual wind tunnel for explosions.
It is.
That's amazing.
It is. So we've covered a lot of ground in this first part. We've explored the why, the what, and the how of blast-resistant design, and we've seen that it's a multifaceted challenge
Yes.
that requires a deep understanding of explosions, blast waves, and structural behavior.
This has been incredibly insightful,
Good.
but I'm sure it's just the tip of the iceberg.
Oh, yeah.
I'm eager to delve deeper into the actual design process in the next part.
Me too. We'll be exploring different construction types, material selection, and all the clever details that go into making these structures truly resilient.
Sounds good.
Oh.
Welcome back. Last time we laid the groundwork talking about explosions and blast waves.
Right.
Now let's roll up our sleeves and get into the actual construction of blast-resistant buildings.
Okay.
What are the building blocks, so to speak, of a structure that can withstand these incredible forces?
Well, Chapter 4 is where the book really digs into the different construction types of materials.
Okay.
And one thing becomes very clear, not all materials are created equal when it comes to blast resistance.
I'm guessing concrete takes the cake, right? It just seems like the tough guy material of the construction world.
You're right on the money. The authors call reinforced concrete the most suitable and economical choice,
Okay.
especially for buildings close to potential hazards where those blast pressures and thermal effects are going to be most intense.
That makes sense.
Mm-hmm.
Concrete is strong and can take a punch, but what makes it so good at resisting explosions specifically?
It's all about how it behaves under pressure, literally.
Okay.
Reinforced concrete can be designed to be ductile, meaning it can bend and deform without shattering. It's like a flexible warrior absorbing the energy of the blast instead of just breaking apart.
So it's like a tree swaying in the wind instead of snapping in half.
Exactly. And the reinforcement, those steel bars embedded in the concrete, plays a crucial role in that ductility.
Okay.
They act like a skeleton holding everything together and preventing the concrete from cracking under those extreme stresses.
Okay, so reinforced concrete is the gold standard.
It is.
But are there any other options for blast-resistant construction?
They do mention pre-engineered metal buildings, or PMs. These are often used for warehouses and industrial facilities because they're relatively quick and easy to construct. But can they really handle a blast? Metal seems a bit more well-fragile than concrete.
You've got to be strategic about it.
Okay.
PMAs can be used for blast-resistant buildings, but there are a few caveats.
Okay.
First, they're best suited for structures located at safer distances from the blast source.
Okay.
Second, they need to be designed with blast resistance in mind.
Okay.
That means using heavier gauges of steel, adding extra bracing, and making sure the connections are strong enough to handle those dynamic loads.
So it's not just about picking any old metal building off the shelf.
No.
It needs to be designed and engineered for the specific threat.
Absolutely. And they also make it very clear what materials are not suitable for blast resistance.
Okay. What's that?
Brittle materials like unreinforced concrete brick or timber.
I can see why those would be a bad idea. They just seem like they'd crumble into a million pieces under a blast. Exactly. Not only do brittle materials break easily,
Right.
but they also create a lot of dangerous debris that can turn into projectiles.
Oh, yeah.
Imagine chunks of brick and concrete flying through the air at high speeds. That's a recipe for disaster.
It's like shrapnel from a bomb. You're trying to protect the building from an explosion,
Right.
and suddenly you have a whole bunch of mini missiles flying around.
Right. And wood, while it might not create projectiles in the same way, is a fire hazard, which is another layer of risk you don't want to deal with during an explosion.
Oh, for sure.
Oh.
Okay, so reinforced concrete is the top choice. And pre-engineered metal buildings can work if they're designed properly.
Correct.
But what about those modular blast-resistant buildings, the ones that are prefabricated and shipped to the site?
Yeah.
Those seem to be gaining popularity.
Yes. The BRMs.
ERMs.
The authors dedicate a good portion of the chapter to those.
Okay.
They offer some unique advantages,
Sure.
especially for remote locations or situations where speed of construction is critical.
I can see how they'd be useful for temporary structures, like those trailers used as offices on construction sites, or even for military applications.
Exactly. But as with any type of construction, the devil's in the details. The authors emphasize the importance of carefully designing the connections between those modules.
Makes sense.
They need to be robust enough to resist blast loads and prevent the modules from separating or collapsing.
And since these modules are essentially self-contained units, you have to think about all the internal systems as well.
Right.
The electrical ventilation, plumbing.
Yeah.
Everything needs to be designed to withstand those forces.
They bring up a really important point about anchoring these BRMs securely to the foundation.
Yeah, I bet.
If they're not properly anchored, a strong blast could turn the entire building into a projectile,
Yeah.
which would defeat the whole purpose of having a blast-resistant structure.
Okay, so we've covered the main construction types.
Right.
Now let's talk about the behavior of materials under those extreme blast loads.
Oh.
I have to admit, materials science isn't my strong suit, but I'm ready to learn.
Well, Chapter 5 gets into the nitty-gritty of how materials respond when they're subjected to those sudden, intense forces.
Okay.
And it's actually quite fascinating.
I'm intrigued. Tell me more.
We all know materials have certain properties like strength and elasticity, but under dynamic loads like those from an explosion, materials don't always behave the way we expect them to.
Oh, really?
They can actually be stronger for a short period of time.
So if you hit something really hard and fast, it might be harder to break than if you push on it slowly.
Exactly. It seems counterintuitive, but think about it this way.
Okay.
If you apply a load gradually, the material has time to deform and maybe even start to crack.
Right.
But if you hit it with a sudden impact, it doesn't have time to react in the same way.
Okay.
Its internal structure can temporarily resist a higher force before it fails.
That's wild. So how do engineers account for this in their designs?
They use something called dynamic increase factors, or DIFs. These are essentially multipliers that account for the fact that materials can exhibit higher strength under those rapid loading conditions.
So it's like a bonus strength boost for materials when they're facing an explosive threat.
That's one way to think about it, but it's important to remember that these DIFs aren't the same for all materials.
Okay.
They depend on the specific material, the strain rate, the temperature, all sorts of factors.
Okay, so it's not just a simple rule of thumb.
Right.
There's a lot of science and calculation involved in determining those DIs.
Absolutely. And the authors provide a lot of detailed information on how to determine those DIs for different materials and loading conditions.
So let's talk about some specific materials.
Okay.
We know reinforced concrete is the star player in blast-resistant design. How does it behave under these dynamic loads?
They go into great detail about reinforced concrete's performance under blast conditions.
Okay.
The key they emphasize is achieving a flexural response.
Go.
That means we want the concrete to bend rather than shear or crack under the pressure.
So it's about designing the concrete to be flexible enough to absorb that energy without failing catastrophically.
Precisely. And the way we achieve that flexural response is through careful detailing of the reinforcing steel.
Okay.
They talk about using doubly reinforced sections where you have steel bars on both the tension and compression sides of the concrete.
So it's like a sandwich with the steel bars as the bread and the concrete as the filling.
That's a great analogy, and that double reinforcement helps to increase the ductility of the concrete member.
Right.
And prevent brittle failure.
They even mention how those rebound forces, the ones that happen after the initial blast wave, can actually reduce the resistance of a singly reinforced concrete member.
Yes, they do.
It's all about anticipating those complex forces and making sure the structure can handle them from every direction.
Exactly. And they also emphasize the importance of shear reinforcement. Concrete is strong in compression,
Right.
but it's relatively weak in tension and shear.
Yep.
Those steel stirrups, those little hoops of steel that wrap around the main reinforcing bars, are crucial for preventing the concrete from cracking and crumbling under those shear forces.
It's like giving the concrete an extra layer of support, making it even tougher.
Right now, what about structural steel?
Okay.
We know it can be used for blast-resistant buildings if those buildings are sited at safe distances.
Right.
How does it hold up under these dynamic loads?
Well, it's metal, so it's strong, but it's also, metal so it can bend and break.
That's the tricky part. The authors stress that ductility is just as crucial for steel as it is for concrete when it comes to blast resistance.
Okay.
In fact, they actually advise against using high-strength steels in some cases.
Wait, really?
Yeah.
I thought stronger was always better.
Not necessarily. High-strength steels can be more brittle, meaning they're more likely to snap under sudden loads instead of bending and absorbing energy.
So in this case, it's better to have a material that can bend than one that breaks?
Exactly. And they also spend a good deal of time discussing the design of connections in steel structures.
Okay.
Those the points where beams and columns come together are absolutely critical for the overall strength and blast resistance of the building.
Makes sense. If the connections are weak, the whole structure is vulnerable.
Right. The connections have to be designed to be both strong and ductile, able to withstand those intense forces without failing or becoming loose. They even provide specific guidance on designing those connections, referencing industry standards like AISC 341, which focuses on seismic design, but has a lot of relevant information for blast resistance as well.
It's all about taking what we've learned from other areas of structural engineering and applying it to this unique challenge.
Absolutely. They also discuss the importance of anchor bolts. Those heavy-duty fasteners that connect the steel structure to the foundation. Again, strength, ductility, and careful design are essential to make sure those anchors can handle the dynamic loads.
Okay, so we talked about the superstructure, but what about the foundation itself? It's literally the bedrock of the entire building.
The authors dive deep into foundation design in this chapter. They explain that soil, unlike concrete or steel, doesn't have much tensile strength, meaning it's not good at resisting being pulled apart.
Right, so you've got to design the foundation to resist those uplift forces that can happen during an explosion. Otherwise, the whole building could lift off the ground.
Exactly. And they discuss different approaches to foundation design, from the simpler static method, which treats the blast loads as if they were static loads, to the more complex dynamic method, which takes into account the inertia of the foundation and the soil.
I bet that dynamic method involves some pretty intense calculations.
It does, but the authors point out that it can sometimes lead to a more economical design, especially for situations where those uplift forces are really significant.
Now, what about masonry?
Okay.
We know it's not ideal for blast resistance, but what if you're dealing with an existing building that has masonry walls? Can anything be done to improve its performance?
That's a good question. They do touch on reinforced masonry, acknowledging that it's sometimes used, but they're very clear that its capacity and ductility are lower than reinforced concrete.
Gotcha.
If you have to use it, they recommend following seismic detailing practices, which focus on strengthening the walls and connections to resist those lateral forces.
So it's like trying to make the best of a less than ideal situation.
Right. And before we wrap up this section on materials, there's one more important concept. Authors introduce deformation limits.
Deformation limits?
Yes.
I'm not familiar with that term.
They're basically guidelines for how much a structure or a component can deform under blast loads before it's considered to have failed. Remember, in blast design, we're not just trying to keep the building from collapsing completely. We're also trying to limit the damage and make sure it's still functional, or at least repairable after an explosion.
So it's like setting a tolerance for how much the building can bend and twist before it's considered too damaged.
Exactly. And they provide specific deformation limits for different types of structures and components based on the material, the type of loading, and the level of protection you're aiming for.
I'm guessing those deformation limits are based on a lot of research and testing.
The authors draw on a variety of sources, including industry standards data from actual blast tests and even sophisticated computer simulations using finite element analysis.
So it's about bringing all the tools and knowledge we have to bear on this problem to ensure that buildings can withstand these extreme events and protect the people inside.
Exactly. And the next part will move from the materials themselves to the methods engineers use to analyze those materials and design those blast-resistant structures. Get ready for some number crunching.
Sounds good. Welcome back to our deep dive into blast-resistant building design.
Glad to be back.
We've talked about the types of explosions, how those blast waves behave, and how different materials stand up to those extreme forces.
Right.
Now let's get into the engineering side of things.
Oh.
The analysis methods used to actually design these structures.
That's where the rubber meets the road. Chapter 6 dives into the world of dynamic analysis.
Dynamic analysis, okay.
Which is all about understanding how structures respond to those time-varying blast loads.
Okay, can you remind me why we need dynamic analysis for blast design?
Uh-huh.
Why can't we just use those traditional static analysis methods that engineers use for, say, a typical office building?
Good question. It's because explosions aren't static forces.
Right.
They're sudden, intense events that create these dynamic pressure waves that travel through a structure.
Right.
So we need analysis tools that can capture that complexity, those changes in pressure over time, and how the building responds to those changes.
It's like the difference between a gentle breeze and a hurricane, right?
Yeah.
You need a different approach to design a building that can withstand a hurricane.
Exactly. And the authors highlight a few key challenges in blast analysis.
Huh.
First, the blast loads we're dealing with are often approximations. We can't predict exactly when and where an explosion might happen or its intensity. So we have to make educated guesses based on risk assessments and historical data.
It's all about managing risk, not eliminating it entirely, because that's often impossible in these complex industrial environments.
Right. And they also point out that the pressure-time relationship of a blast wave is almost always simplified in our calculations.
Right.
We usually represent it as a single straight line, even though the actual pressure changes over time in a more complex way.
So we're simplifying the problem to make it more manageable, but that simplification comes with some inherent inaccuracies.
Exactly. And then there's the challenge of structural modeling.
Okay.
To make the analysis easier, we often break down a complex structure into smaller, simpler components.
Okay.
Walls, floors, beams, and so on.
That makes sense. It's like breaking down a big problem into smaller bite-sized pieces.
But the authors caution that this uncoupled approach, where we analyze each component separately, doesn't always capture the full picture.
Right.
It doesn't fully account for the way those components interact with each other in a real-world blast event.
So it's like trying to understand how a car works by looking at the engine, the wheels, and the transmission in isolation without seeing how they all connect and work together. You might miss some important interactions.
That's a great analogy. And while there are more sophisticated methods that can account for those interactions, those are usually reserved for situations where a very high level of accuracy is needed.
Okay, so let's talk about some of those simpler methods that engineers typically use for blast analysis.
Okay.
What's the most basic approach?
The most basic approach is the equivalent static method.
Equivalent static method.
As the name suggests, it involves treating those dynamic blast loads as if they were static loads.
Wait, so we're basically pretending the explosion is a constant force, like the weight of the roof, even though we know it's a dynamic event.
In a way, yes, it's a very simplified approach that ignores a lot of the complexity of a blast event. It doesn't account for things like time-varying loads, material behavior under dynamic conditions, and so on.
Right.
But it can be useful for very preliminary design or for situations where the blast loads are expected to be relatively low.
But I'm sensing that the authors aren't big fans of this method.
They're not. They point out its significant limitations and caution against using it for most blast design applications. They really advocate for using more rigorous methods that capture the dynamic nature of the event.
So what's the next step up in terms of complexity and accuracy?
The next step is the single degree of freedom, or SDOF method.
SDOF.
This is a more robust approach that takes into account the dynamic characteristics of the structure or component we're analyzing.
Okay, break it down for me. What's a single degree of freedom system?
Imagine a simple mass attached to a spring. That mass can only move in one direction, up and down.
Okay.
That's a single degree of freedom now in structural engineering. We can represent a more complex element like a beam or a wall, as an equivalent SDOF system.
So we're essentially simplifying the structure, representing it as a system, with just one way to move to make the analysis easier.
Exactly. And the key to the SDOF method is figuring out the equivalent mass, stiffness, and damping of that simplified system.
Okay.
The authors provide some helpful equations and tables to help us do just that.
So it's like translating the real-world complexity of the structure into a language that our dynamic analysis methods can understand.
That's a great way to think about it. And once we have those equivalent properties, we can use equations of motion to calculate how the structure will respond to that blast load over time. We can determine how much it will deflect, how much stress it will experience, and whether it will exceed those deformation limits we talked about earlier.
It's like predicting how the structure will dance under the pressure of that blast wave.
Exactly. And the book even walks us through a step-by-step numerical integration method for solving those equations of motion.
Oh, wow.
It's like a recipe for analyzing a blast-resistant structure.
That's SDOF. But I remember you mentioning something called multi-degree of freedom systems. What are those all about?
Those are for the truly hardcore engineers. Multi-degree of freedom, or MDOF systems, are used to model even more complex structures that can move in multiple directions.
Like a...
Think about a whole building frame with columns, beams, and floors all interconnected.
That's a lot of moving parts. I can see why that would be a lot more complex to analyze.
It is, and the authors point out that MDOF analysis methods are much more computationally intensive than SDOF methods.
Right.
They often require specialized computer programs to solve those equations of motion.
So this is where those finite element analysis tools come in.
Right.
I've heard that term thrown around, but I'm not quite sure what it means.
Finite element analysis, or FEA, is a powerful technique that lets engineers model the behavior of really complex structures under various loads, including blast loads.
So if I understand correctly, FEA involves creating a virtual model of the structure, breaking it down into thousands or even millions of tiny elements.
Right.
And then running simulations to see how those elements interact and how the overall structure responds to the forces.
Exactly. It's like taking an incredibly high-resolution X-ray of the building and seeing how all the stresses and strains flow through it when a blast wave hits.
That sounds incredibly powerful, but I imagine it also requires a lot of expertise and specialized software to do it properly.
It does. The authors provide some guidance on using FEA for blast analysis, but they emphasize that it's a complex tool that requires a deep understanding of structural mechanics and numerical methods.
So it's a tool for the specialists, but it's fascinating to know that it exists and that we have these incredibly powerful ways to analyze and design blast-resistant structures.
Absolutely. Now remember, all of this analysis is just one part of the design process.
Right.
We're figuring out how the structure will behave under blast loads.
Right.
The next step is actually designing those components, the beams, columns, walls, connections, to withstand those loads.
Right. We need to make sure those components are strong enough, ductile enough, and detailed correctly to handle those forces. And that brings us to Chapter 7, which I'm guessing dives into all those practical design considerations.
You got it. Chapter 7 really gets into the nuts and bolts of design. The authors start by laying out some general principles, like using appropriate load combinations,
Okay.
accounting for dynamic effects, and making sure those connections are robust enough to transfer the forces.
It's a good reminder that a chain is only as strong as its weakest link.
Exactly. And then they break it down by material, providing specific design guidance for reinforced concrete, structural, steel, reinforced masonry, and even soil.
Soil.
Yes.
We usually think of soil as something we build on, not something we design.
True, but soil plays a crucial role in supporting those foundations. The authors highlight the importance of understanding how soil behaves under dynamic loads and how to design foundations that can handle those uplift forces we talked about earlier.
Makes sense. If the foundation fails, the whole building goes down with it.
And they even talk about designing for projectiles, those flying objects that can be generated during an explosion.
So we're not just protecting the building from the initial blast wave. We're also protecting it from those secondary impacts that can happen afterward.
Exactly. They provide guidance on evaluating the impact resistance of different materials and designing protective measures like barriers and shields. It's like building a suit of armor for the building.
Now, Chapter 8, if I remember correctly, is all about detailing, which sounds like where the rubber really meets the road in terms of turning those design calculations into real-world construction details.
You're exactly right. Chapter 8 is all about the nitty-gritty details, how those components are actually connected, reinforced, and assembled. Right. They provide a ton of illustrations and guidelines for detailing reinforced concrete connections, structural steel connections, and connections for those pre-engineered metal buildings.
I was flipping through that chapter, and they cover some really specific things like using oversized washers to connect cladding to framing and different types of anchors for masonry. It's amazing how much detail goes into these designs.
It really is. They even have a section on designing blast-resistant doors and windows.
Oh, right.
Which are obviously critical for protecting the occupants inside.
I can see why those would require some specialized considerations. You don't want the doors and windows becoming the weak points in your blast-resistant design.
Hey, they talk about using blast-resistant glazing, reinforcing those frames and connections, and making sure they're properly integrated into the overall building envelope.
Okay, so we've covered new construction. But what about existing buildings that weren't designed with blast resistance in mind? Can anything be done to improve their performance?
That's a really important question, and the authors address it head-on in Chapter 9, which is all about retrofitting existing structures for blast resistance.
Yeah, that's a very practical topic. Not every building starts with blast resistance as a primary design consideration, so it's important to know how to improve their resilience after the fact.
Absolutely. And the first step, they say, is evaluating the building.
Okay.
Identifying potential hazards, determining the blast loads it might be subjected to, and assessing the vulnerability of the existing structure.
So giving the building a blast resistance checkup.
Exactly. And then they outline a range of upgrade options from strengthening existing components and connections to installing those catch systems that can prevent debris from injuring occupants.
They even mention using new blast-resistant elements to shield existing components. It's like adding an extra layer of protection around those vulnerable parts of the building.
And they get into the specifics of how to upgrade different systems.
Okay.
They talk about strengthening structural connections, reinforcing metal panel walls and roofs, and even upgrading those concrete masonry unit walls that are common in many older buildings.
It seems like there's a whole toolbox of options for improving the blast resistance of existing structures, depending on the specific needs and constraints.
Absolutely. And they even cover upgrading windows and doors, using those blast-resistant glazing materials, and making sure the frames and connections are up to the task.
So we've covered the theory, the analysis of design, and even the retrofitting of blast-resistant buildings. But what about seeing it all come together in a real-world project?
That's where the last two chapters come in.
Okay.
The authors really bring it all home by walking us through a couple of detailed design examples. Chapter 11 focuses on a shear wall, building a common type of structure in the petrochemical industry.
It's like getting a behind-the-scenes look at how an experienced engineer would approach this type of project.
Exactly. They show us the calculations, the load combinations, the material selections, the detailing. It's all there.
And then Chapter 12 takes us through the design of a metal building, which presents its own unique set of challenges.
Right. And to round it all out, they even include an example of a masonry retrofit design, showing us how to evaluate an existing masonry wall and design different upgrade options.
This book really does cover the full spectrum of blast-resistant building design. I mean, an incredible journey exploring all these concepts and seeing how they're applied in real-world situations.
I agree. It's a testament to the ingenuity and dedication of engineers who are working to make these critical facilities safer and more resilient.
So as we wrap up this deep dive, what are the key takeaways you want our listeners to remember?
First and foremost, blast-resistant building design is not just about protecting structures. It's about protecting people. It's about creating environments where those who work in potentially hazardous industries can do their job safely and with confidence.
We've seen how understanding the different types of explosions, the behavior of blast waves, and the response of materials under these extreme loads is essential for designing these structures effectively.
And we've learned about a range of analytical tools, from those simplified methods to those incredibly powerful computer simulations that engineers use to predict how buildings will perform under these dynamic conditions.
And we've seen how even existing buildings can be upgraded to improve their blast resistance, using a variety of techniques and materials.
This deep dive has given us a glimpse into a fascinating field of engineering that is constantly evolving and advancing to meet the challenges of a complex and sometimes dangerous world.
If our listeners want to dive deeper into this topic, we highly recommend picking up a copy of Design of Blast-Resistant Buildings in Petrochemical Facilities. It's a wealth of information, and it will give you a newfound appreciation for the engineering that goes into creating these structures.
And remember, our conversation today was just our interpretation of the book's contents.
Right.
We encourage you to explore the book yourself, engage with the material, and come to your own conclusions.
Thanks for joining us on this deep dive. Until next time, stay curious and keep learning.